Um, Thanks for inviting me. Thanks so much. I'm really happy to have this opportunity to speak to you today. I can imagine being in Japan. Um, Hopefully, I will get to visit sometime soon for real. And today, I'm going to talk about a line of work that I started probably like 5 years ago now. About generating programs from types. So by the way, if you have questions during the talk, I'm happy to take those as well, or you can save them until the end. Both is fine. Okay, so let's begin. So what is the goal of this whole line of work, right? So our sort of overall goal is to automate programming with the idea that if we automate low-level tedious parts of programming, then we would be able to build software faster and with fewer errors. And of course, this is not a new idea. The field of programming languages have been working at it for multiple decades now, right? So, and we've done a pretty good job of it. So, for example, when we moved from assembly to C, we automated things like calling conventions, right? Memory accessing, and the whole class of bugs went away with that level of automation, right? And then we invented higher level languages like Haskell, for example, and we automated away things like memory management, right? And the whole class of bugs went away again. So the question that I'm asking myself in my work and in this talk is, what is next? So what is the next step? Or perhaps, Haskell is the pinnacle of creation. Who knows? I happen to be a big fan of it. And so what is that next big leap, right? That would allow us to raise the level of abstraction even more, right? To make programs even more concise, even less error prone, even more natural to write. And in fact, I would argue that the closest thing that we have today to programming of the future is Stack Overflow, right? So on Stack Overflow, you can express whatever you want to write, the purpose of your program in a high level way with natural language, right? Maybe give a couple of examples, and a couple of days later, an answer comes back, right? So you could ask, for example, something like, how do I split a string on a custom separator in Haskell? And someone will probably post a solution, right? This works great, except that, of course, you have to wait a couple of hours to a couple of days, right? And we are using precious human time to do this. What we would like to do is to automate this. So the vision that I want you to have in your mind is, how do we build this automatic programmer's assistant, right? That can help us solve these small, tedious programming problems. And this is where the field of program synthesis comes in, right? So program synthesis, the idea is we want to allow programmers to describe what they're trying to do using some kind of high-level specification, and then automatically translate the specification into an executable program. And the way we're going to do this is through search, right? So the way program synthesizers are different from compilers is that the gap between the specification and the program is so large that direct translation is sort of impossible. And instead, we give a synthesizer a big space of programs to search in, and it performs some search and finds a program that satisfies the specification. So today I'm going to focus more about, what should these specifications look like, right? So how should programmers express their intent to the synthesizer? Program synthesis researchers have tried many things, right? Many ways of expressing intent. So we tried definitely input-output examples is a popular way, some kind of logical specifications, assertions, pre-post conditions, even natural language. And these are all great, and they have their own, advantages and disadvantages. In this talk, I'm going to argue for a different kind of specification that I particularly like, and this type of specification is types. So why don't we use types to describe to the computer the computation that we want to perform, right? And if you are, like me, a Haskell programmer, this idea wouldn't sound crazy to you at all. Haskell programmers routinely use Google to search for code, right? So if you're unfamiliar with Google, it's an API search engine for Haskell. So here is the Google website. And here I can enter a type, and it will search for library functions with that type, right? So for example, remember our very first example was we want to split a string on a custom separator. So we can express that to Google as, we want a function that takes a character, which is the separator, which takes a string and returns a list of strings, right? And even though it might seem that, well, we just gave a type, right? We didn't really give all that much information. As you can see, Google actually found some really useful functions for us, right? So if you look at this one, called uninterspersed, in fact, does the right thing. The second one's called split. It's from maybe some obscure library, right? But apparently someone already implemented this functionality that we can just use out of the box, right? Of course, the downside of Google is that it just searches for existing library functions out there, but not every programming task has already been solved by someone, right? So it doesn't completely solve our goal of automating Stack Overflow, right? But it gets us very close. But the point of this demonstration was that, in fact, types are a really natural and effective way to communicate your intent to the synthesizer, right? So why in particular I like types as a kind of specification, right? So first of all, I argue that they're programmer friendly because many programmers already familiar with types, right? They program in typed languages and they use types not only for bug finding, but also for tasks like API search, right? This is what I just showed you. And also often types are more concise than some other kinds of specification like input-output examples. Types are also informative in the sense that they are more precise than natural language. And also over the years, programming languages researchers have developed so many different type systems that can augment this kind of simple types that I just showed you, right? With different kinds of properties that we can use in our specifications. And finally, types are synthesizer friendly in the sense that they actually can help you search, right? And in this talk, I will show you a little bit what I mean by that. All right, so, and in this space of type-directed or type-driven synthesis, right? This is really not just a single point, right? This is a whole landscape, because, like I said, we have invented so many different type systems over the years, right? So you can have this landscape between more simple types and more expressive types, right? Where the simple types would be more programmer friendly because they are more familiar to the programmers, but also more ambiguous in the sense of how precisely they specify the program, versus the expressive types would be less programmer friendly and less ambiguous, right? And in this talk today, I want to actually explore this space a little bit. I will start with showing you a tool called SyncWith, which is more on the expressive type of the spectrum, right? Which takes as input refinement types and can synthesize recursive functional programs from those. Then I will briefly demonstrate an extension to SyncWith, which is sort of even more, the specification is even more expressive. We add some information about resources to those types. And what we get in return is we get more guarantees. We also get the guarantee that the programs that we're generating are efficient. And finally, at the end, I will show you our recent work on a system called Google Plus that is more on the simple side of the spectrum. It takes as input Haskell types, just like Google, and it can synthesize function compositions from others. Okay. Let's start with part one, SyncWith. And by the way, this appeared at PLDI 2016 if you want to know more about this work. Okay, so this part will be split into two. I will first show you how to use types as specifications, and then I will briefly talk about how the search actually works and how types help us search. Okay, so the running example we're going to be using in this part of the talk is inserting an element into a sorted list, right? So the program that we want to write, the task that we want to solve is that we have an input and a list, and the list is sorted, and we want to compute an output list where the X is at the appropriate position, right? So this program, this task can be solved using a recursive program, which I will currently show you using, it's not any kind of real programming language, it's sort of a toy little functional language that Sync-with, this tool, uses, right? But it's similar to Haskell, but just a little bit different. So we want to write this function insert that takes an element X and list X's as arguments. So the first thing that it has to do is it has to match on the input list X's. If this input list is empty, right, which is denoted here with a nil constructor, we simply return a singleton list with X in it. And if it's not empty, then we'll have to compare the new element X with the head of the list H. And if X is less or equal than the head, then we have found the right place to insert it. So we simply prepend it to the list. Otherwise, we'll have to call insert recursively on the table. Okay, this is the program that we want to obtain, right? But let's say we don't want to write it by hand because, well, there's all these, different cases that we have to take care of and whatnot, right? So can we somehow ask the computer to generate this program for us automatically from its type? Okay, so this is what we want to achieve. We want to generate this code on the right from some kind of high-level specification and a program space, right? A search space, which in this case, the program space is simply a set of components that the synthesizer is allowed to use in the program, right? So here it will be like list constructors and primitive operations like less equal, right? So what kind of specification can we give to synthesize this kind of program? So I told you before that types are our specifications, right? So let's start from, an ordinary kind of Haskell-like type for insert. So this type would be something like A, which is an element of any type, to list of A's, and then the output is again a list of A's, right? If you are actually a Haskell programmer, you would know that this is not enough. In Haskell, you would need to specify a type class constraint, which would allow you to actually compare the list elements with inequalities. But for now, in this part of the talk, let's ignore that and just assume that all elements of all types are comparable. All right. So, but what do you think would happen if we just give this simple type to Sync-with as the specification, right? So we actually don't have to guess that. We can go to the Sync-with web interface and try that, right? So here I simply defined the list data type, right? So I said that a list is either nil or const, which is just a very standard definition of lists in functional programming. And then I said, well, please give me a function insert that takes an X of type A, a list X of type list A, and returns a list of A's, right? So if I run that, unsurprisingly, I get a very uninteresting program, right? So Sync-with just tells me, oh, well, I mean, you can just return the input list, right? Which is not what we want, right? So either this can happen, or maybe can return something like always return an empty list, right? So one of those very uninteresting things is going to happen. And why does this happen? That's because the specification that we gave it is ambiguous, right? The specification doesn't really tell us neither that the output list must be sorted, nor what kind of elements is it supposed to have, right? And that's why Sync-with sort of is free to return any program that has the type that we gave it, and it searches the program space from shorter programs to longer programs. That's why it tends to return this very short but very uninteresting programs. Okay, so what is the solution to this problem of ambiguous specification? Well, the solution that Synquit takes is to give more power to types, right? So why don't we make our type system more expressive so that we can add all these extra properties to rule out the uninteresting programs? Okay, so the kind of properties that we want to express in our specifications would be something like this, right? So we have an input X, which is anything, but we also have an input list X's that is sorted, right? And by the way, the output should also be sorted, and the elements of the output should be the elements of X's and X, right? So here by elements, I mean the set of elements in the list. So if you are following carefully, you would notice that this is not a complete specification. There are programs that satisfy the specifications and do something else. For example, they would not, they might duplicate some elements. But for now, let's say that this is the property that we care about, right? And the question is, so now I just expressed this to you informally, can we express this kind of specification as a type? And turns out we can, and there's already a really neat type system out there that can express these kind of properties, right? And I'm talking about refinement types, in particular the flavor of refinement types from Liquid Types paper. So what are these refinement types? The refinement types are types annotated with simple predicates, right? So for example, this type int out here can be annotated with this predicate to say that an element of this type has to be greater or equal to 0, right? So here, the predicate is called the refinement. And so by refining type int with this predicate, we can specify basically the type of natural numbers, okay, this way. So far, it doesn't seem very interesting, like what can we possibly specify with this little simple predicates? Well, it turns out that by combining this with polymorphic data types, you can express really interesting properties with very simple logic, right? So for example, we can stick this type of natural numbers inside a list, right? So here is the type that is the type of lists of natural numbers. So if you think of it, if you think about this, something kind of magical just happened, because we just expressed that in our list, all the elements are greater or equal than 0 without using any quantifiers, right? So usually if you try to express something like this, not using types, but using pre and post conditions, you would need a quantify formula. And once you have quantifiers in your logic, automatic verification is problematic, right? So here we can express those universally quantified properties without using quantifiers. And so it turns out that by combining the simple predicates with recursive data types, you can express very interesting invariants on your data structures, again, without using any quantifiers, right? So for example, remember our type of lists. So I will show you how to add basically one simple predicate to this type to describe instead the type of sorted lists, right, as we need for our insertion example, right? So let's first rename this type into slist, that stands for sorted lists, right, and rename it everywhere. But so far, we didn't really do anything, right? So in particular, this definition is wrong because we say, well, an empty list is always sorted, which is true, right? But we also say that a non-empty list is sorted as long as its tail is sorted, which is not true, right? So that's not enough for the list to be sorted. So there is another property that has to hold, right? And the property that has to hold is that the head of this list, this guy, is actually less than equal than everything in the tail. So how can we express that with refinement types? Well, note that this, the type of the tail is actually polymorphic, right, in the type of elements. This type variable A could be in principle substituted with something else. And that's exactly what we're going to do. We're going to say, a tail is a list of elements that are greater or equal than the head, right? And so in this way, by adding one simple predicate, you can describe the type of sorted. So now that we have this type, we can actually write a more precise specification for insert, right? So we can say X is sorted, the output is sorted, and we also refine the output type of this function with the following predicate. We say that, with a predicate about the elements, right? Where here, this elements is something called a measure, which is basically just a restricted form of recursive function over list. And so now that we have this specification, we can ask Synquit to synthesize this function for us. Let me see. So here I defined sorted list just like I showed you on the slides, right? I also defined what length of the list means and what the set of elements of a list mean using just basically recursive functions. I also gave Synquit a component that compares elements for inequality that it can use in the program. And so now if we specify insert this way and we run it, then we get the actual insert program that we were looking for, right? Cool. So we were able to express our intent to the synthesizer. Just a little bit about how this actually works, right? So how does Synquit find this program? And it finds it pretty quickly. Right? So as I mentioned in the very beginning of the talk, program synthesis is search, right? So essentially we'll have this specification and we will have a set of components, and the synthesizer will be systematically enumerating programs that it can construct out of those components, essentially until it encounters one that satisfies the specification, that type checks against the type. This is a very high level view. So as soon as I tell you this, you're probably wondering, well, this cannot possibly work because there must be a lot of different programs that you can construct out of this component. Indeed, this is the main challenge in program synthesis, is that the program space is usually very large, right? So in particular, if you're considering enumerating programs in the order of size made of these components that we have, then there will be about 2 to the 70th programs of a size equal to or less than our solution, right? So this is sort of how many programs the synthesizer would naively have to explore. And this is a very big number, basically, right? And this would never work. So program synthesis is basically like trying to find a star in the universe, right? And the name of the game is, can we somehow, with a single check, eliminate big parts of the search space, right? So that we gradually hone in on our solution, right? And the key idea is that we have to design our type system and our type checker in such a way that we can reject hopeless programs early, meaning during construction. Okay, let me illustrate what I mean by that. So in the picture that I showed you before, right? So we sort of constructed the full program and then type checked it against the specification. And then if it doesn't type check, we reject it. And in fact, if we use the original type checker that was proposed for these refinement types, this type checker sort of works bottom up, right? It infers the type of the whole program and then can compare it to the specification, which would mean that we have to construct the whole program before we can check whether it satisfies the specification. And that, of course, is not very good for synthesis, right? So what we did in our work is essentially change the way type checking of refinement types works to make it more top-down, right? Essentially, so that it can take the specification and propagate it down through an incomplete program And so in this way, it is able to reject these hopeless programs before they are fully constructed. And by doing so, it also rejects all the programs that essentially have the same prefix, right? So let me illustrate this on our example. So this is our specification for insert. And let's say the synthesizer starts enumerating these incomplete programs. So at first, the whole program is completely empty. Of course, at this point, it's not yet hopeless, right? There's nothing we have done wrong yet. Let's say the top level construct that the synthesizer proposes is a match on X's. At this point, still not hopeless, right? So we can, so there's no evidence that it's not possible to fill in those branches to satisfy the spec. But let's say the synthesizer decides to fill in the first branch with nil. Well, at this point, informally, you can see that this program is hopeless, right? Because we know that the result of insert has to contain X, no matter what, right? And we're returning nil in one of the branches. Well, so in fact, and by the way, if we are able to reject this program, we are automatically rejecting about 2 to the 50th other programs that start with this fragment, but have different subterms for the second branch, right? And we definitely wouldn't want to enumerate all of them. So this is how our type system would reject this program, right? So it would sort of start with the overall specification. So we know that the body has to have this type, right? And so meaning that the first branch has to have this type as well. And at this point, it would issue some constraints, right? That basically in this case say that the elements of nil, which we know are empty, right, should be equal to the elements of X's, which are also empty, union X, right? So this is the constraint so this is the proof obligation that we have to prove, right? And then we can give it to an SMT solver, and of course it will say that this is invalid, right? Because an empty set cannot be equal to an empty set union single. Okay, so we have just rejected this hopeless program early. But this was sort of a simple case, right? Because obviously we just had 2 branches, right? The first one was filled, the other one was unfilled. So it's kind of very easy and natural how to propagate these constraints just down the branches. The hard part actually is, can we also do sort of more fine-grained propagation and propagate those constraints through function applications, right? That's actually the hard. So imagine a different partial program that we now want to reject. So let's say our synthesizer already guessed the nil branch correctly, but let's say in the cons branch, it's trying the following thing, right? So it's trying to prepend the head H to the result of insert X into some unknown expression, right? So intuitively, this program is actually hopeless, right? So why is this program hopeless? Well, even though we don't know what goes here, right? So we don't know what elements this resulting list is going to have, but we can disprove that this list is sorted. Why? Because for this list to be sorted, we need H to be smaller than everything in the tail, everything in this guy, right? But this guy already contains X, right? And we have no relationship between H and X, right? So this list we cannot possibly prove that this list is sorted. Can I remove this annotation? Okay, cool. So but this sounds like, pretty elaborate reasoning, right? So how would our automatic type checker be able to figure this out? So let's see, it's actually not that complicated. So again, we will sort of hone in on this branch, right? And we're trying to type check it. We're trying to prove that this list is sorted. Okay, so to do that, well, we'll look at the type of cons, right? And in this case, we know that to type check this cons, we need to type check its tail against this type, right? So we need to prove that everything in the tail is greater or equal than age. So now looking at the type of insert, right, which is also polymorphic, now we know that in order for the result of insert to have this type, we need to instantiate this tau here with, you know, this type up there, right? With this. And so, which means that X also has to have this type, right? So now we know that X has to check against this type, meaning that we need to basically prove that X is greater or equal than H, right? So this is the constraint that we're generating. And of course, SMT solver will say this is invalid, right? Because we haven't enforced any relationship between X and H, right? So basically what we're saying is, well, you first have to make a comparison between X and H to be able to fill this expression. Okay, cool. So we can reject this partial program as well. So, and that was it for the first part. I'm wondering if there are any questions at this point. I guess people could post questions on the chat if they want, or
So perhaps I can ask a quick one. So one thing that I was wondering is whether so okay, you create a solution for, you know, generating programs from types, and that's very cool. But I wonder if you don't create some other problems while doing this, in particular some reusability problems, because what you have is that you're defining these new sorted lists, which is a different data type from lists. And then you have to define new operations for these sorted lists and so on. So, and now you have this, you know, you have to create a bunch of other infrastructure, and you cannot just reuse the operations that you have on your standard lists. Okay,
yeah, this is a really good question. So in fact, yeah, the way I showed you the definition of sorted list here, it was a separate data type. In fact, so Synquit supports something called abstract refinements, which I shouldn't have done this, which basically allows you to parameterize the list type by a predicate, right? So in particular, we can just have a general list type that is parameterized by both the type of the elements and by a binary predicate, basically A2 bool, that you essentially here you would use this predicate of H and nu instead of a concrete relation, right? So if you add enough of those indices to your data types, you can create a very general list data type that you can then instantiate. If you instantiate it with, you know, less than equal, then you get sorted lists. If you instantiate it with something like not equal, you get unique lists with unique elements. If you instantiate it with true, you get regular lists.
Okay.
So you can do that. But of course, your question in general is very valid, right? So there is a whole infrastructure of these different refined types and measures and things that you have to build to be able to use the synthesizer. That this is totally valid. What you get in return, though, is that your programs are also verified correct, right, against these specifications. So in a sense, you have to, like, from the point of view of what you get, you have to compare this with against, you know, having to write the program and write the spec and verify the spec, right? Yeah, so I think that would be a more fair comparison. Does it make sense?
Thank you. Thank you.
Okay, let me proceed with the second part where, right, I want to talk about synthesis.
Sorry, there's another question on the chat. Yeah.
Okay, simply rejected and we'll start over. or is it used as a hint? Oh, this is also a really good question. So essentially, I think what the question is about is, so we have rejected this program that I just showed you, right? Even though it was almost correct, right? So what in fact we should have learned from this is, sure, we can do that, except that we need to wrap it in a comparison, right? So we need to wrap it in the conditional. And this is not something that I was planning to talk about, but this is in fact exactly what Synquit does, right? So it has this mechanism called condition abduction. So essentially, when it runs into a problem like this, where the current branch does not verify, but it can abduce, basically it can guess a simple condition that would, like this, right? That would make this branch verify. It simply wraps this expression in this conditional, right? In sort of eager way, and then continues to synthesize the else branch. So, and then afterwards, when the program is synthesized, it would prune useless branches, right? That didn't actually contribute to the program. Yeah, great question. Cool. Thanks for your questions. So yeah, let me talk about resin. So what we have just seen, right, is you give Synquit this refinement type, it generates a program, it actually guarantees that the program is correct on all inputs, right? But functional correctness is not the only thing that we care about, right? So another thing that we might care about is whether this program is efficient, right? And Synquit absolutely has no guarantees about that, right? It will just return the shortest program. And to demonstrate when the shortest program might not be the most efficient, so let me show you this example. So essentially here, we are trying to implement sets as strictly sorted lists, right? So this S list type is just like the previous one, except it's strictly sorted. And what we're trying to implement is set intersection, right? And we also assume that somewhere in the environment, we have a member function that takes an element and a list, and it returns a Boolean whether the element is in the list or not, right? So if we ask to generate an intersection of two sorted lists, we get this program that is pretty simple and short, right? So what it does is it would match on the first list. Obviously, if it's empty, it will return an empty list. Otherwise, it will check if the head of X's is a member of Y's, and depending on that, we'll either include it or exclude it, right? This program is correct. However, it's not the most efficient program, given that the lists are actually sorted, right? So let's go back here. So we got this program on the left that has a quadratic complexity, right? Because it has to go over the list wise for every element of X's, right? Whereas for sorted lists, there actually exists a linear implementation, which sort of does this intersection in sort of like a zip-like fashion. But this linear implementation is longer, right? So that's not what Synquit would generate by default if it has access to this member component. So basically, this is where this work on resin comes to the rescue, right? So I'm going to tell you about how can we express program efficiency in our type specification, and how can we use this extra annotations to guide synthesis, right? And this this stuff has been published in our PLUI 19 and ICFP 20 papers. Right, so what we have now in Synquit, right, is we can say, you know, we can basically express in a type something like find the intersection of two sorted lists, and we get a short program with quadratic complexity. What we want is we want to be able to say, find the intersection of two sorted lists in linear time, right? And then get that program with linear complexity, right? So how are we going to do this? Well, how are we going to, can we express this additional constraint as a type? Well, yes, and the recipe again is we want to give even more power to our types, right? So we want to make them extra expressive. to be able to add this information. So the way our type system that we call resquare for refinements and resources does it is recall that this is what our refinement types look like. So we add one extra annotation to our types, right? In addition to refinements, which are logical predicates, we also add a numeric term to every type that we call potential, right? Essentially, this, you can think of it as sort of an amount of fuel that that is stored inside every value of this type that can then be used to pay for operations, right? To pay for computation steps. And again, the same magical thing that I told you about with refinements happens here, right? So on the one hand, this doesn't seem like something very complicated, right? This is just the type of natural numbers with potential 1. However, you can stick this type inside a list. And now all of a sudden, you get a list where every element has potential 1, meaning the whole list as a whole has a potential equal to its length, right? So basically, you can expect that it's a list with linear amount of potential using a very simple annotation, right? Just a constant annotation. And so we can use these annotations now to restrict our type of intersect, right? So we can say that, oh, we're just going to give a linear amount of potential to the first list and a linear amount of potential to the second list, right? And we will also do the same thing to the member function to also annotate it to say that it takes linear amount of resources. And so this type will be enough to prohibit that inefficient implementation. So I'll just show you very quickly. So this one takes a little bit longer to synthesize, so that's why I already pre-filled it for you, right? So essentially what happened here is, as you can see, like I said, we annotated both input lists, gave it, each one of them potential of 1, right? So this one also says that this recursive call costs 1. And the annotation for members says that members also takes sort of the resources that we count here are the number of recursive calls, right? So here we're saying recursive call costs 1, and here we're saying, well, the member also traverses this list linearly, right? So that's why it requires this list to have a linear potential. And so if you give it these annotations, then in this case, resin will generate this longer implementation that is linear, right? We don't have time to go into details, but you know that is what happens. So how does this happen? Well, essentially, exactly the same idea as I had before, right? So this enumerating programs and rejecting hopeless programs early, except now we are doing it with these resource types, right? So we are doing this this top-down type checking with resources, right? So essentially, just at the high level, the way it's going to work is we will start with this specifications for intersect, and we want to deem this program, this incomplete program that doesn't have the second branch filled in yet, we want to deem it hopeless because we already made 2 calls, one to member with Ys, right? And one to intersect also with Ys, right? And we know that there is not enough potential in our list Ys to make both of those calls, right? Because both of those calls are require, you know, one unit of potential per element of Ys. And more specifically, how it's going to happen is, so you see now we have these 2 occurrences of Ys in our program, the blue one and the green one, right? So when we first generate them, we sort of give them a type with unknown potential, right? P and Q. And we will try to solve constraints for what these P and Q could possibly be, right? So, but the constraints that our type checking generates is, first of all, that the total amount of potential available, which we know here is 1, should be partitioned into P and Q, right? So it's an affine type system for those of you who know what that means, right? So whenever we use a variable multiple times, we have to partition its potential. The second constraint we're going to generate is that P is enough to call member, right? And remember, our member had, it required the Y's to have 1 unit of potential per element. So we know that P has to be greater or equal than 1. And Q must be enough to call intersect, right? So now Q has to be greater or equal than this potential here, right? So Q also has to be greater or equal than 1. And of course, we can give those constraints to an SMT solver and we'll say that it's unsat, right? So we cannot find possibly potential annotations to that would work here, so we can reject this program. Okay, that's all I wanted to say about resin. And in the last 10 minutes or so, I'm going to talk about Google+, right? So on the other side of the spectrum, basically more on the simple ones. So about in the first two synthesizers that I showed you, right, Synquit and resin, it's kind of impressive that they can generate this programs with strong guarantees. However, they have very important limitations, right? So one limitation is that, of course, those types are hard for programmers to write, right? Because they have all these refinements and resources and whatnot, and they're just not regular types that everyone uses every day. And secondly, even though we have this smart type checker that can reject populist programs early, it still doesn't really scale to large component libraries, right? And so in this work, we're sort of trying to address both of those limitations. Okay, so the challenges that we faced when building Google+ is first scaling to larger libraries, which is the first one I'm not going to talk about here. So this is the underlying algorithm which we use to make it scale better is described in our Popl 20 paper, which you are welcome to read. I will instead tell you about the other two challenges, right? So the other two challenges is overcoming ambiguity, right? Remember, in the beginning, I told you, oh, simple types are not enough as a specification for synthesis. But now somehow we're saying, oh, no, that's exactly what we're going to use. And the third challenge is, even though these types are more programmer friendly, they're still, for some programmers, especially for beginners, they're still not the most. So how can we help beginners come up with these types? Okay, and this, what I'm going to talk about here is covered in our UPSLA 20 paper. Okay, it's just a reminder, the inspiration for this work is Hugo, right? Which is something that Haskell programmers use all the time to search for API functions by their type. However, Google can only return a single function that implements, that has a certain type, right? That implements a certain functionality. But sometimes the function that you need has not been written yet, right? And instead, to achieve the functionality that you want, you need to compose multiple functions from the library. And so Google cannot do that for you. And we want to do that instead. So here's an example of where that would be needed, right? An example of something that Google cannot do for you. Let's say I want to compress a list. And what I mean by compress is I want to remove adjacent duplicates, not all duplicates, but just adjacent ones. So for example, if I have an input list like 1, 1, 2, 1, then what I want to get as output is 1 to 1, right? So the adjacent ones got removed, but that one at the end stayed. So in fact, in Haskell, you can solve this problem by just combining a couple of library functions together. So the simplest way to do it is you can call group on the input list, which would produce a list of lists that groups equal elements together. And then once you have that, you can map head over that list of lists to get the first element from each group, right? And that's how we can compress a list. The specification that we want to use is just the ordinary Haskell type of that function, right? So perhaps the first attempt to determine its type would be just list to list. However, again, this is not enough in Haskell if we want to be able to compare list elements by equality, which is what we need to do to determine whether the JSON elements are equal. We need to also add this type class constraint, right? So we want list elements to be equatable. So this is the specification that we want to use to synthesize our program. So we have developed a system called Google Plus, where you give it a specification like this, right? And you give it a bunch of popular Haskell libraries, and it comes up with a list of programs for you, right? That are likely the programs that you want that have this type. So let me just quickly show you the demo of Google Plus, right? So what we wanted to do here is to search by type. So we can do a QA, the list of A's, and say search. And Google Plus will come up with some programs for us that has this type. So see, the first one is not really what we're looking for. The second one, also not really. And by the way, to determine whether it's a program that we're looking for, Google Plus is also giving us some examples, right? So for example, this one, how do we know it's not what we're looking for, is because on the list 1.1, we expect it to return just a single one, but in fact, it returns the same list unchanged. This one also doesn't look very promising, right? Because this list, it does not preserve. It's similar, not this one, but here is the program that we were looking for, right? So it eliminated 1 from here, eliminated 0 from here. So it found the program we were looking for at a number 4. Okay, so of course, the challenge is still there, that the type is very ambiguous, right? So how do we overcome this ambiguity in Google Plus? Well, the thing is, if you try to do this search naively and simply return the list of all programs, let's say in the order of their size, that type check against this type, you will be in big trouble, because you'll basically get a flood of completely uninteresting programs, right? So you will get something like this. As you can see, these programs here, if you're familiar with Haskell, are really not what you're looking for. And moreover, they are sort of obviously irrelevant, right? We should be able to eliminate them without any additional input from the programmer. So why are they obviously irrelevant? Well, this one, for example, always crashes, right? This program takes the head of an empty list, crashes on all inputs. In fact, this program is an answer to any type query whatsoever, right? Because head of an empty list has any type. But even other programs that don't always crash sort of seem irrelevant. So for example, this very first one here just returns an empty list. It completely ignores its argument, right? Which is probably not a good sign. So in Google Plus, we make this fundamental assumption that all the arguments are relevant, right? So the user wouldn't give you an argument if they didn't mean to use it. So we would like to eliminate programs like this, right? But even these two, the other ones that seemingly use, that they do use their list argument, they ignore the type class constraint that the user gave, right? This is also part of the relevancy requirement. The user would not give us a type class constraint if they didn't mean to use it. And those programs don't actually require the type class constraint. They don't compare list elements for equality. And even if we eliminate these types of irrelevant programs, there's still one kind left. Those are duplicates, right? So for example, these two programs have exactly the same behavior, right? Because what they do is they group the input list, and then they take the first group. So this first group will always be a list of identical elements, right? And then whether we exclude the last element from that group or the first element from the group, since it's a list of identical elements, doesn't matter. So we don't want to show the user programs that are duplicates. So how do we approach this in Google Plus? How do we filter out these irrelevant programs? Well, we actually just use test-based filtering. So once we generate the candidates, we use property-based testing tools like Quick Check and Small Check. would test those candidates. So we would check properties like, does this program crash on all inputs? Is the output always the same as another earlier candidate? And whether the output stays the same if you change the input, right? So, and then we can find, if we find counterexamples to these properties, then we display the program. If we cannot find a counterexample to one of the properties, then we filter this program out. And of course, it can have false positives, right? Because we're not testing on all inputs, on infinitely many inputs. But what we discovered is that it's always better to miss a couple of programs than completely overwhelm the user with irrelevant programs every time. Okay, and the benefit of using this test-based approach is that once we can use those generated test inputs to demonstrate program behavior to the user, right? In the demo, I showed you that Google Plus displays some short inputs that demonstrate behavior of generated programs, and in particular, the inputs on which the different candidates differ from each other, right? So for example, we know that, this is the program that we want because on this input 0, 0, it just returns 0, unlike all of these previous programs. Okay, cool. And the last thing I want to tell you about is how we help beginners come up with types like this, right? Because this type is sort of not completely trivial. It has this type class constraint, right? So sometimes types involving higher order functions are kind of hard for beginners to come up with. And what we found is that, in general, beginners, it's much easier for them to come up with a test, meaning an input-output example, rather than a type. So what we added to our tool is a component that can infer types from tests, right? So I will quickly demonstrate this here. So let's say I didn't know how to specify a type for my DDAL function, but instead I can just add some tests, right? So I can add my test from the slide before, right? 1, 1, 2, 1 should give me 1, 2, 1. And let me add another test with a different concrete type just for fun. So for example, ABBA should map to ABA, right? And now if I hit search without specifying the type, what would happen is Google Plus will suggest several types that I might have meant as a specification. And voila, the type that we actually meant is here. And as you can see, there were only 3 different types suggested, which was pretty manageable. So how does that work? To be able to do this, we essentially start from the tests that the user suggested. We use GHC to infer the concrete types of these tests. Then we use anti-unification to come up with the least common generalization of these different test types. In this case, it would be something like A to A with an ORD constraint. And then from then on, we know that the user might have meant this least common generalization, or they might have meant even more general type, right? So we basically explore the lattice of all types that are more general than that. And among those types, we sort of filter out the ones that are clearly irrelevant. So for example, these types here are irrelevant because they generalize over a complex type, like a list. Or
Nadia, sorry to interrupt. I just wanted to point out that we are running out of time. So if you could wrap up in the next few minutes.
Yeah, definitely. That's basically for only a couple of slides. Okay, so we filter out irrelevant types, and we come up with a nice short list of types to suggest to the user. Okay, I just wanted to mention that we ran a user study with 30 participants. Each participant solved 4 different programming tasks that are of the sort like the compressed task I showed you. And each participant first solved 2 tasks with Google and then 2 with Google Plus. And so what we found is that our participants solved 50%, about 50% more tasks with Google Plus than with Google, right? So it really helped them solve the tasks. And moreover, when we looked at how they provide specifications to the system, it turns out that actually a lot of people wanted to use tests only to specify their problems. So we actually had to use this type inference feature that we implemented. And among beginners, this result was even more pronounced. Okay, that's it. That's all I had. So today I told you about these 3 different systems that generate programs from types with types of different level of expressiveness and different kinds of properties that they can express. Thanks for your attention.
Okay, thank you very much, Nadia. So we have time maybe for 1 or 2 questions. I guess we already asked a couple of questions during the talk, but if there are some more questions now, we can take 1 or 2 questions. You can either write them down on the chats, either Zoom or Slack, or if you want, you can also turn on your audio.
Oh, I see someone has the hand raised. Hiroyuki?
Okay. Can you hear me?
Yeah, we can hear you.
So I am very interested in your talk, and I think your talk is targeted for some functional languages like Haskell or subset of OCaml. So, and do you think this approach can be applicable to other like imperative languages like Java or C++ or something? How do you think?
Yeah, really good question. So first of all, the component-based synthesis stuff, right? Like that is similar to Google Plus. There are already this previous work doing this for Java, right? This, for example, this tool called Sciped that does this component composition stuff in Java. In some sense, it's easier because the type system is not as expressive. So in particular, they don't even handle polymorphism in their tool, which makes the search much, much simpler, right?
Oh, I see.
On the other hand, if you're talking about the other two, like the more expressive systems like Synquit and Resin, so I actually have sort of a parallel line of work on generating imperative heap manipulating programs like C programs from separation logic specifications, which are not exactly, that they're not really types, but they sort of have a similar flavor.
Thank you. I see.
Oh,
so there's another question on the chat.
Yeah. In the program synthesis with complexity, if the required complexity is impossible, yeah. So the really good question. So right now, essentially Resin would either fail or go into an infinite loop, right? Trying to search for a program that is not there. So we sort of, one of the future work directions that we want to pursue is of course something like optimization, right? Where you don't have to provide a bound, but rather it would, let's say, start by synthesizing a program without a bound, right? And then once it finds one, it tries to sort of tighten it by coming up with a tighter bound itself, right? And then and then if it doesn't find anything, it sticks with the original one. If it does find one, it tries to search with an even tighter bound. So there we would run into this problem, right? Where we would need to somehow efficiently determine that there is no program with this constraint. And I think there's some recent work from Loris D'Antoni's group on proving unrealizability of synthesis problems that I think could come in handy here, but we haven't explored that yet.
All right. Okay. Thank you very much. I think we should stop here. So let's give a virtual round of applause to Nadia.
Thanks, Bruno.
And thank you very much for the very nice invited talk. And we will have the next session in about 25 minutes. Okay, thank you.
Thanks again for inviting me.
You're welcome.